Welcome to AP Biology. This video is on spontaneous processes. Spontaneous processes are going to be processes that take place without an input of energy. Instead, they usually release energy. In order to determine whether or not a process is spontaneous, we have to determine delta G. G is the amount of free energy. The amount of free energy is the amount of energy actually available to perform work. So basically it's the total amount of energy minus the amount that gets lost as heat, because we know that heat or thermal energy is not actually usable. There's a difficult and a simple way to determine delta G. The more complicated equation we see up here, delta G, or the change in free energy, is going to equal the change in enthalpy. Enthalpy is going to be the total change in energy minus the temperature times the change in entropy. And if we look at this part of the equation right here, the temperature times the change in entropy, we're talking about what's not usable or what's lost as heat. So all this equation really means is that the change in free energy is the change in total energy subtracting from it the amount that's lost as heat or the amount that's unusable. There's a simple way to determine delta G. You take the free energy final minus the free energy initial. If this number that you obtain is negative, that means that that process is spontaneous, meaning it can occur without an input of energy. Instead, it's going to release energy, and that released energy can be available to perform work. Here we see some basic examples. We have a diver on the top of a diving board. When he's on the top of the diving board, he has lots of potential energy. Let's say we give him an energy of 10 units, whatever those 10 units actually are. He dives off the diving board, lands in the water, and now he has a lower amount of energy. He only has 2 units of energy. If we were to determine delta G, you would take the final 2 minus the 10 initial, and you would obtain a delta G of negative 8. That means that this process is spontaneous. It doesn't require any input of energy for the diver to fall from the diving board to the water. It would happen spontaneously. What actually is free energy? Free energy is a measure of a system's instability. The more unstable something is, the more free energy that it contains. In a spontaneous process or a spontaneous change, the system is going to go from an area of instability to an area of stability. Or in other words, it's going to go from high energy to low energy. When it reaches maximum stability, we say that that system or that process is in equilibrium. Equilibrium is a state of maximum stability. So a spontaneous process that's going from instability to stability, or going from high energy to low energy, is moving towards equilibrium. Here we see the 2 types of reactions that can take place within metabolic pathways. Reaction 1 is exergonic, reaction 2 is endergonic. In an exergonic reaction, which is the reaction you see on the top here, high energy reactants are broken down into low energy products. This is going to have a release of energy. Since it releases energy, we consider exergonic. That's the definition, a reaction that releases energy. If we were to calculate delta G, the products minus the reactants, or the final minus the initial, delta G would be negative. Since delta G is negative, we know that exergonic reactions are spontaneous. An endergonic reaction is the opposite. You have high energy products and you have low energy reactants. So these reactants are being put together. They are being used to build this high energy product. So you're going uphill. In order to do this, you need an input of energy. Endergonic reactions consume energy, or they need an energy to be put into the system. Delta G would be positive. So this process or this reaction is non-spontaneous. We said that in a spontaneous process, the system is working towards equilibrium, or going from instability to stability. We can look at this taking place in two types of systems, a closed system or an open system. Living organisms are always open systems, and we're going to see in a second why that's so crucial. A closed system has the ability to reach equilibrium, and once equilibrium has been met, that system can no longer be used to perform any kind of work. Here we see an example of a closed system. This is a hydroelectric system, and remember, to be closed means that matter and energy are not transferred between the system and its surroundings. So this hydroelectric system is totally enclosed, and we have water in two tanks, and the water in the high tank is higher in energy and the lower tank is lower in energy, or this is more unstable and this is more stable. So the water is going to move from an area of high energy to low energy. And as the water flows down from the high drum to the low drum, it is going to be used to spin the water wheel, and the water wheel is used to light up the light bulb. Well, this works fine initially, but eventually the water is going to reach an equilibrium. And once that water has met equilibrium, it can no longer be used to perform work. It's a good thing that living organisms are not closed systems, because once equilibrium would be met, no more work could be performed. Instead, living organisms are open systems, where they constantly transfer matter and energy between the system and their external environment. So here you see an open hydroelectric system, and you see that water enters the system, water exits the system. This is a pretty simple analogy, right? We know that energy enters the body of a living organism, or enters a cell as food, and energy is going to leave a cell or leave a living organism as heat. As long as food enters an organism, or in this case as long as water enters the hydroelectric system, that water is going to flow from high energy to low energy, or it's going to flow to an area of less stability to an area of more stability. And as long as that water is flowing downhill, it can be used to spin the water wheel and generate electricity. This example that you saw right here, this would be one reaction. This would be an exergonic reaction, because it has a high energy reactant being broken down into a low energy product, or it's going downhill and it's releasing energy. And the energy released is being used to power the light bulb. This example we see on the bottom here, this would be a catabolic pathway. Catabolic pathway is made up of multiple exergonic reactions, each releasing energy, each being able to power the light bulb. Here you see the importance of food. Food is the source of all energy that enters the body. Heat is going to be the source of all energy leaving the body, and as long as that food is being broken down, as long as it's moving from areas of less stability to areas of more stability, working towards equilibrium, it can be used to release energy and fuel all of our metabolic processes. This completes this video.